Our objective in this section is to apply the rules of differentiation and to take higher derivatives. Let's start with notation. If we're talking about a function y equals f of x, the way we write what the first derivative is either y prime, the derivative of y, or f prime of x, the derivative of f. Y prime is how we say it, f prime of x. D dx means the derivative with respect to x of whatever follows, in this case of the function x. So this part right here is the derivative with respect to x, the derivative with respect to x of a function x in this case. We can also say the derivative with respect to x of y, or d dx of y, and for short, write dy dx. You'll see it a lot in all of these forms. When we take the second derivative, or the derivative of the first derivative, that adds a prime, so y double prime, or f double prime of x, or the derivative with respect to x of the derivative with respect to x of f of x. Notice we have two d's, so d squared, two dx's. Remember, dx is like the delta x, so when we say dx and we square it, because it's one variable really, it's just dx squared. So d squared dx squared of y, or the second derivative with respect to x of y, or d squared y dx squared. It works that way for first, second, and third derivative. Anything fourth or higher, instead of continuing to add the prime notation, we, in parentheses, put the number of the derivative. So this is fourth derivative of y, fourth derivative of f of x, fourth derivative of y, similar. Okay? Now let's talk about some rules. Remember that derivative means slope of the tangent line. If we start with the constant rule, finding the derivative of a constant. Let's take a constant function, for example, like y equals 3. What does that look like graphically? Just a horizontal line. Well, what is the slope everywhere along this horizontal line? That's right, the slope is always 0. So when I take the derivative with respect to x of a constant, I will always get 0. For example, let's say I'm taking the derivative with respect to x of 3. That's a constant, I get 0. If I say y equals 5, what is dy dx? The derivative of a constant is 0. The power rule. The power rule says x to a number can be treated this way. I take the number, it gets multiplied to the front, and I subtract 1 from the exponent. For example, if I'm taking the derivative with respect to x of x to the 5th, I take the 5 that is the exponent, it gets multiplied in front, and I reduce 1 from the exponent, 5 minus 1, or simplified to be 5x to the 4th. The constant multiple rule. Remember how in limits, we can take any constant that's multiplied to the function and pull it outside of the limit expression? Well, since a derivative comes from a limit expression, we can do the same thing for a derivative. Pull it outside of the derivative expression. For example, the derivative with respect to x of 2x to the 5th. Well, the 2 is a constant multiple, so I'm going to pull that out of the derivative expression. 2 times the derivative with respect to x of x to the 5th. X to the 5th. When I take the derivative of x to the 5th, remember we got 5x to the 4th? So there's my derivative. Now, of course, we want to pretty that up a bit. 2 times 5 is 10, so really 10x to the 4th is the best answer for that one. Similarly, in the sum and difference rules, if we're taking the derivative of a sum or difference of functions, I can break that up into the derivative of one of the functions plus or minus the derivative of the other function, just like with limits. For example, let's say y equals 5 plus x to the fifth. What will y prime equal? Take the derivative of each one at a time. The derivative of 5 is 0. The derivative of x to the fifth, 5x to the fourth. Remember when we did that earlier? Then I can pretty it up. 0 plus 5x to the fourth is just 5x to the fourth. And then we've got our sine and cosine rules. The derivative of the sine function is the cosine function, and the derivative of the cosine function is the negative sine function. If you check out their graphs, you'll see that. But memorize these. Let's take a look at some examples. Differentiate where appropriate. Differentiate means take the derivative. Hint, sometimes you may need to rewrite the expression first, such as in the first one. We will remember to use proper notation, of course. So here's a function, find the derivative of y with respect to x. First, we're going to rewrite this so we don't have a quotient. Here's what I mean. X can be a common denominator into both parts of the numerator. Then I can simplify it so I don't have a quotient. 3x to the negative 1 minus x squared over x makes x. So what did we do here? We did a rewrite to not have a quotient. Now we can take the derivative of this using our power rule. Remember how that works? One at a time. We'll take the exponent, multiply it in front, subtract 1 from the exponent when we take the derivative. So I can write dy dx, the derivative of y with respect to x, equals, multiplying the negative 1 out in front makes negative 3, subtracting 1 from the exponent for x makes negative 2. Then I'm going to go on to this one. Well, x is like x to the first. Multiply the 1 out in front and subtract 1 from the exponent. X to the 0. Well, what is x to the 0? That's just 1. So really, this is negative 3x to the negative 2 minus 1. So the derivative of x will be just 1 because of the 0 exponent. Then, even though this is the derivative, we can pretty it up a bit. So I don't really like to leave negative exponents, especially because later when I'm plugging in numbers. So we'll pull it back downstairs and then minus 1. Although this is also a good answer, we can say, yep, I have a derivative, or I can keep going further and get a common denominator. Negative 3 minus x squared over x squared. Both of these are acceptable answers. Even this one with the negative exponent is an acceptable answer. Let's take a look at another one. Here's another example of when we should rewrite it first. So I'm going to say f prime of x equals, and I'm going to change this radical notation right here to exponent notation, x to the 2/3. Make sure you're comfortable with rewriting radical to exponents and vice versa. 1 over 2 x to the 2/3 can change to 1 over 2 times x to the negative 2/3, bringing that x up to have a negative exponent. Now remember the constant multiple. Oh, I'm sorry, I put a prime there. That's not correct. I don't have a derivative yet. Let's get rid of that prime that's there. F of x. Now I will go to f prime of x, the derivative of f of x. Remember, when we're working with constant multiples, we can ignore them and do this derivative first. Leave the 1/2 there. Do the derivative of this part by multiplying by the negative 2/3. And then subtract 1 from the exponent. Negative 2/3 minus 1 is 3/3, so that I have a common denominator. Let's finish writing what that makes. 1/2 times negative 2/3 x to the negative 5/3. Simplifying this a little bit, I have negative 1/3 x to the negative 5/3. And although all of these versions are a version of the derivative, it's a little bit better if we rewrite this without negative exponents. So maybe I put the x back down in the denominator, like that. That's a good answer. If I sometimes have to choose the radical form, know how to get it back into radical form. And there we have it. In the next one, we have a combination of functions. Remember our sum and difference rule. This is asking us find the second derivative. So we have to do it twice. Let's do dy dx, the derivative of y with respect to x first. So negative 4 hangs out in front while we take the derivative of the cosine. The cosine function's derivative is negative sine x. Then we have the other piece, constant, so the derivative is 0. Derivative of the constant is 0. So there's our first derivative. If we simplify it, is 4 times the sine of x. Second derivative, or d squared y dx squared, keep that constant hanging out in front. The derivative of the sine of x is the cosine of x. There's our final answer for the second derivative. Number 4, we're given a function. This is not saying raise it to the 6th, it's saying find the 6th derivative. So we're going to have to do this derivative 6 times. Let's start with f prime of x. Derivative of sine x is cosine x. Why don't you pause it and see if you can do this on your own. Alrighty, welcome back. We've got f double prime of x is the negative sine of x. The derivative of the cosine is the negative sine. Third derivative, the negative derivative of sine is cosine, so that negative is still there. Fourth derivative, look at how my notation changes a little bit, becomes the derivative of negative cosine is negative of negative sine x, or sine of x. Fifth derivative is cosine x, and notice how we're wrapping back around the derivative of cosine x, negative sine of x. There we are. We can put that answer in that blank. Last one from an AP test. Function is sine of x. What's f prime of pi over 3? What this means is first we have to find f prime of x. Then we plug in that value. So f prime of x is cosine x. Then second, we plug in x equals pi over 3. So here's what that looks like. F prime pi over 3, that means the cosine, because cosine was the derivative of the sine, with pi over 3 plugged in, so the cosine of pi over 3, and we know that's 1/2 because we're really good at our unit circle. Finally, another AP problem on the free response part. So that means show all the work, show all the work, show all the work. For what values of k and p? That's what we're looking for at the end. Will f be continuous and then differentiable at x equals 1? Well, remember continuous. We've spent a long time in the last chapter talking about continuity. So continuous means that the limit as x approaches what value? Well, continuous polynomial, but piecewise, possible break at 1. So as x approaches 1 from the left, for our function has to equal the limit as x approaches 1 from the right for our function, because remember the limit has to exist. We can't have any jumps, breaks, holes. So let's find those two limits. From the left is this part, so I'm going to plug 1 in to this expression from the left. From the right is this part, so I'm going to plug 1 in to that expression. Let's simplify this as much as we can. 2 minus 1 is 1 equals 1 plus k plus p. I guess the best I can get to is 0 equals k plus p, but I need to know k and I need to know p. One equation is not going to do it here. Let's look at the other side of the story. The function has to be differentiable, also differentiable. That means there are slopes. We can draw tangent lines. The tangent lines we can find their slopes. basically what we want to know is that the limit of the derivative of the function coming from the left is equal to the limit of the derivative of the function coming from the right. This is the way to show that the slopes are going to be the same from the left, slopes are the same from the right. Really, we just want the derivative on the left to equal the derivative on the right. We don't want different slope here than it is here, and then we get a sharp point. That is not differentiable. We do not want that. So let's do the derivative of the piece on the left. On the left is 2x minus x squared. So the derivative of 2x minus x squared at x equals 1, that needs to equal the derivative of the piece on the right, from the right, that piece, x squared plus kx plus p at x equals 1 as well. So let's do that derivative first. 2, because that becomes x to the 0, which we know is 1 or seems to disappear, minus using our power rule, 2x. We still are going to need to plug in x equals 1. Over here, the derivative is 2x plus k is a constant, plus p is a constant, so that derivative becomes 0, and that's going to be at x equals 1. Now we can go ahead and plug 1 in on each side. So 2 minus 2 times 1 equals 2 times 1 plus k. Let's see, over here it looks like we get 0. 2 plus k, so it looks like k equals -2. Now we can use that, go plug it in on this side, and then if 0 equals -2 plus p, it looks like p equals 2.